did struggle, though, with what I should say to this community. Much greater depth of knowledge on many of the aspects that are so critical to sea level than I have. But sea level is a very broad issue, and I decided what I'll start with was sort of the standard sort of talk I would give about sea level, and then moving on to what are some of our requirements which we hope this community can continue to provide and improve into the future. So sea level is not only a scientific issue, it's a major societal issue. Where's the keyboard gone? Our society is a coastal society. Particularly over the last 10,000 years, we've developed in a period of stable sea levels, or last 6,000 years, a period of stable sea levels, and in many places, falling sea levels. So today, there's about up to 150 million people living within 1 metre of current sea level, and about $1 trillion of GDP generated in that same 1 metre of sea level. This is just an example. The Gold Coast in Queensland, southern Queensland, where in 1940 there was about 40,000 people there. Today there's 500,000 people living in this area with 4 million visitors a year. That was the 2010 numbers. So it's a major issue, how sea level will change over the future. So the first thing to look at is, well, what has happened to sea level in the past in warmer periods? We all know that during ice ages, sea level was substantially lower than it is today. But what about in past warm periods? So the left-hand column here is present-day sea level. So CO2 values have increased from roughly 280 parts per million to over 400 parts per million. Sea level has risen, but only about 20 centimetres so far. But we know the climate system is out of equilibrium, and sea level is not in an equilibrium situation either. If you go back to the last interglacial, then sea level was probably somewhere between 6 and 9 metres higher than present day, at temperatures roughly equivalent, maybe a little bit more, than where we are today compared to pre-industrial temperatures. And much of that rise came both from Greenland, but also a contribution from Antarctica. Go back 400,000 years, then temperatures were perhaps a little warmer again. Sea level was higher. CO2 values, both in the last interglacial and 450,000 years ago, were somewhat similar to pre-industrial temperatures. Go back to the Pliocene. The information is less well constrained, but sea levels were higher, perhaps up to 30 metres, maybe even higher than current values at temperatures a few degrees higher than where we are today. Temperatures towards where we're heading by the end of this century if we have no significant mitigation. Jumping now forward to the last few hundred years, so from about 2,000 years ago until the present sea level, or to the pre-industrial period, sea levels were relatively stable globally from the limited information we have. Shown here is the tide gauge records in the three coloured lines from about 1900 or a little bit before 1900 up to the present. The satellite altimeter record in blue. A few tide gauge records averaged in the sort of purpley colour, and then individual paleo information from various geological indicators of sea level. So clearly, the rate of rise has increased from the pre-industrial period, where the changes in sea level were a few tenths of a millimetre per year, up to the 20th century, where it's the order of 2 millimetres per year, and then into the satellite record of 3 millimetres per year. So the 1901 to 1990 rate is estimated to be 1.5 millimetres with an uncertainty of 1.3 to 1.7. the Hay et al. Reconstruction, which has come out since the IPCC report, said 1.2 millimeters over this period, so the order of 20% less than what we had in our estimates, but with the uncertainties overlapping. And then the satellite record, of course, estimating 3.2 millimeters per year, although I will revisit that later, and I'm sure Chris will talk about that later today. Note, however, that there are also high rates of sea level rise in our relatively poor estimates of global average sea level that we can reconstruct from global tide gauges during the period 1920 to 1950. The satellite altimeter record has been critically important in improving our understanding and improving the motivation to understand sea level, in that it's been really the first time we've had a global picture of the regional distribution of sea level and how that varies in time. So we've always known that sea level is not constant, it won't rise uniformly, it will vary, but we haven't been able to quantify that adequately until we have the altimeter record. And this shows the 1903 to 2004 period, average rate of rise of just over 3 millimeters per year, but some regions, the rate of rise is the order of 10, 12 millimeters per year in the western equatorial Pacific, and close to zero in the eastern Pacific and places like Southern California. So what are the causes for global mean sea level change? Firstly, there's the warming, cooling of the ocean, thermal expansion, contraction of the ocean. That's the dominant, or one of the dominant factors in the 20th century, and likely to be the dominant factor in the 21st century. There's the change in mass of glaciers and ice sheets. Glaciers are probably the largest single contribution during the 20th century, and likely to be the second largest contribution during the 21st century. There's a limited mass in glaciers that can be lost, the order of 44 centimeters, so their contribution in the long term is limited. And of course there's the ice sheets, which have much greater contribution or potential for contribution on the longer term. We recommend the term barostatic for this term. Eustatic has often been used, but it's been used in different ways, and we think it's just confusing, and we're recommending using the term barostatic for changes in mass of the ocean. This changes in liquid water stored on land, so there's the climate components of that, and there's a note coming out in Science, I think, this week on the climatological components of that, but there's also the anthropogenic components of that, and that's the pumping of water from aquifers, the depletion of these aquifers, and much of that water ultimately making its way into the ocean, and also the storage of water in terrestrial reservoirs that have been built, particularly during the second half of the 20th century. Of course, relative sea level is what people living at the coast are interested. I, as trying to understand what's happening, I'm interested in the change in volume of the ocean, but what people really need to understand is the change in relative sea level relative to the land. And that's affected by changes in the ocean circulation, changes in the land movement, the redistribution of mass on Earth, and therefore the changes in the gravitational field, further changing sea level. Our understanding of sea level has improved dramatically over the last, I'd say, 1 to 2 decades. This shows the budget for the last period, for the satellite altimeter period from 93 to 2010. One of the conundrums that has faced successive decades of researchers is an inability to really understand the reasons for 20th century sea level rise. So if we just focus on the altimeter period, thermal expansion is the largest contribution, and so the model estimates and the observational estimates are shown in black and red. The glacier contribution is the second largest contribution. The Greenland ice sheet and the Antarctic ice sheet, we have model estimates of the surface mass balance and also of the dynamics, but those dynamics are not as robust in those models for projecting sea level change over this period. And there's changes in the land water storage. Adding all those together, then the sum of contributions from the model and the observational components is shown in the second last line there. And then the observed change in global mean sea level rise. So there's at least a consistency now between what we estimate to be the contributions to sea level change and the observed change. That applies to some extent to the 20th century as a whole now, although perhaps less well understood in the early parts of the 20th century. A revised satellite altimeter record, which Chris will talk about and I'll touch upon, has a slightly lower rate, but still consistent with, and in fact slightly better consistent with the sum of contributions than the standard rate. I hear my phone's going. If you add those components together, the sum of observed components is in the yellow and the satellite altimeter record in red. Then within the uncertainties, these two are equal. There are some differences in trends and there are differences in the interannual variability, which would be valuable to be better able to understand these differences. And if we turn then to the model components, then the black solid lines are the sum of all the contributions that we can model together, not including the ice sheet dynamical terms. The individual grey lines are individual models going into the CMIP5 archive, which were used in IPCC AR5. And then if we add on the observed dynamical contributions from the two ice sheets, then you get the dotted line. So over the total period, the amount of rise is similar, but compared with the satellite altimeter record, the time history of that is by no means identical. So there's clearly a greater understanding than there has been in the past, but by no means a perfect fit. Looking forward into the 21st century, then the projections here are from effectively from 1996 through to 2090, so roughly 95 years, for the four different scenarios that are used for projecting into the future. RCP 2.6 is a scenario which requires major greenhouse gas mitigation, and it is the only one of these scenarios that comes close to meeting the Paris target of 2 degrees Celsius warming by 2100. Our emissions are currently on tracking along the highest of these scenarios, RCP 8.5. And then if we look at the components from that, ocean thermal expansion is given in red for each of these, glaciers in the light blue. So they're the two dominant contributions to the 21st century. There's a surface mass balance, particularly for the Greenland ice sheet, increased surface melting, increased loss of mass from the Greenland ice sheet. The dynamical component is also positive for Greenland, but for Greenland, the glaciers can retreat from the coastline or largely can retreat from the coastline, limiting the ocean ice sheet interaction, which is a dominant forcer for the dynamic response, and therefore limiting that response into the longer term. Antarctic, we expect increase in snowfall on Antarctica, leading to some offsetting of sea level rise from other contributions, but an increasing dynamical contribution associated with a warming ocean and a melting of ice shelves from that warming ocean, allowing faster flow of glaciers into the ocean. There's also a component from land water storage. Again, that's poorly quantified, but we expect a dominance of mining of water from aquifers over the building of dams. In fact, the building of dams and the storage of water in terrestrial reservoirs has slowed considerably over the last decades, and we expect that to continue into the future. The ice sheet dynamical and land water contributions are scenario independent in these projections, not because that's what we think will happen, but because we actually don't have enough information to separate between those different scenarios, or we didn't at the time of the AR5. So what do the projections mean? So this is the projections relative to 1996 through to the end of the 21st century. For RCP 8.5, that's a sea level rise of 53 to 98 centimetres over that period. In contrast, RCP 2.6 is a sea level rise of 28 to 61 centimetres. These only start to really diverge significantly by mid-century. So there's a lot of disequilibria in the climate system which is contributing to an ongoing rise even if there is significant mitigation. For RCP 2.5, the rate of rise increases during the early parts of the 21st century and then stabilizes and begins to decrease by the end of the 21st century, but will continue for many centuries, even with the major mitigation. However, if we have unmitigated emissions, then the rate of rise increases throughout the 20th century, reaching rates of 8 to 16 millimetres per year. So this is approximately the same rate as sea level rose during the last major deglaciation of the Earth, when sea levels rose at 1 metre per century for many millennia, with peak rates perhaps as high as 4 metres per millennia. Early emissions lead to larger sea level rise, so delaying mitigation is not good for sea level rise. Largest contributions, I think I've said, thermal expansion and glaciers, then Greenland surface mass balance and the Antarctic and Greenland dynamics. And as I said, two of these terms are scenario independent in the current projections. One of the major uncertainties is the potential for significant ongoing and accelerated contributions from the Antarctic ice sheet. And the dynamics of that are shown here. The penetration of warm water underneath the ice shelves, melting them at the base, allowing this grounding line to retreat shoreward on a slope which gets deeper as you go back from the coast, allowing accelerated outflow from the ice sheet and an ongoing unstable situation. So once you get onto this bottom slope, which gets deeper as you go back from the coastline, it's unstable. The ice sheet either has to retreat further or advance. So our estimate was only this mechanism that could lead to a substantially larger rise during the 21st century than in our projections. We had trouble quantifying what that was. This was a very difficult and controversial issue in trying to formulate an appropriate way of communicating the information and its uncertainty. Our estimate was that it would not exceed several tenths of a metre per year. We didn't really know what several tenths of a metre was. You can read the relevance part of the chapter, and the highest estimate is about 0.6 of a metre above our central projections. But we didn't want to put that in the headline statement because we knew that would be the headlines, even though we gave it very low probability. And current evidence doesn't allow the quantification of either the timing or the onset of the magnitude of a multi-century contribution from a rapid decay of the Antarctic ice sheet. Post AR5, there's been quite a lot of work focusing on what the dynamic contribution to sea level could be. They're shown here. We were aware of some of this work was coming at the time of the AR5, but it wasn't published in time for us to be able to use it and include it. So the AR5 estimate was between -2 and 18 centimeters, 18.5 centimeters by 2100. So Pine Island Glacier, there's two estimates here, 2.5 centimeters and 2 centimeters by 2050. The Thwaites Glacier, 2.5 centimeters by 2100, and the Thwaites was a major concern, considerable more ice that could come into the ocean than for the Pine Island Glacier. In East Antarctica, Lambert and the Totten, again, a couple of centimeters. All of Antarctica, Conford made an estimate of up to 20 centimeters by 2100, and Anders Leverman, these are actually results we'd hoped to use but weren't published in time, had a range of 4 to 21 centimeters for RCP 8.5 and 2 to 14 centimeters for RCP 2.6. So they're not that different from what we'd actually specified for our likely range in the AR5. However, there is a significant implication here. The ongoing retreat of the Pine Island and the Thwaites Glacier and a couple of the other nearby glaciers in East Antarctica implies an unstable situation and likely an ongoing contribution from these ice sheets well beyond, or from these glaciers alone, well beyond 2100 and for centuries. Sea level rise will not be uniform. There's a number of contributions to that. Firstly, there's the ocean dynamics, changes in ocean circulation, changes in winds, means a regional redistribution of sea level. In the top panel here is the average from the CMIP5 models. We used about 21 models that were available at the time of the report. And so you see these areas of higher sea level rise at the poleward ends of the subtropical gyre in the North Pacific and also the Atlantic, and also across the southern Indian and South Pacific Ocean. A lower rate of rise right near the equator, right near the Antarctica, and we believe these are associated with changes in wind patterns. And there tends to be a greater rate of rise in the Arctic, but in the bottom panel is the differences between those models, and there's actually greater uncertainty, particularly in the Arctic region. A change in pattern in the North Atlantic associated with changes in the thermohaline circulation of the Atlantic Ocean. But there's also other responses, the ongoing glacier isostatic response, which is important, particularly in the high latitudes of the northern hemisphere. So the east coast of US would expect a higher than global average rise from this effect, whereas Stockholm the projections are for little relative sea level change as a result of the rising land from in response to former ice sheets. Fingerprints associated with changes in mass distribution from both glaciers and ice sheets, resulting in a sea level fall right near the ice sheets as a result of reduced gravitational attraction and a vertical movement of the land, and a larger than global average rise in the far field. And that's particularly evident here for the ice sheet contributions, where this larger than average rise throughout the Pacific, much of the equatorial Pacific, and into the Indian Ocean. When you add all these contributions together, then for the 4 different scenarios, these are the regional distributions of sea level change. So again, you see this high in sea level across the polewards ends of the subtropical gyres in both hemispheres, higher than average rise along the east coast of the US, actually sea level falls in the high latitudes around Greenland, Hudson Bay, etc. And similarly around the Antarctic Peninsula. However, when you look at this from the point of view of where people are living, then it's likely that in about 95% of the ocean, sea level will rise, and about 70% of the coastlines will experience a sea level rise within about 20% of the global average rise. So for first approximation, the global average rise is actually a very good first indicator of what you might expect locally. There's lots of people doing regional projections. We've done them for Australia. We've done them for other regions as well, and other people have done that as well. Sea level rise will not stop in 2100. It will continue to rise for many centuries. We don't have the same type of information that we had for 2100 to be able to do likely or try and quantify in terms of uncertainty the projections. So what's shown here are the range of projections available in the literature. And we've divided those into different scenarios, again, because of limited information. So for the high scenario here, then for by 2300, we're talking of sea level rises between 1 and over 3 meters. Only for the very lowest scenario might we be able to limit that rise to less than a meter by 2100. All of these models likely underestimate the ice sheet contributions, both during the 21st century, well, not so much during the 21st century, but in the longer term. On the centennial time frame, they likely underestimate the ice sheet contributions. On the longer time frame, the amount of rise is dependent on the temperatures that we get. For thermal expansion, there's approximate linear relationship in equilibrium between sea level change and temperatures. The glaciers only have a limited amount of mass and therefore can only make a limited contribution to sea level. Greenland, I think, is a critically important issue. There is a threshold. Beyond that threshold, surface melting exceeds increases in accumulation of the Antarctic ice sheet, leading to an ongoing decay of that ice sheet over centuries to millennia. Exactly where that threshold is not well determined. This shows one example, which is the only study we have, which combines both surface mass balance changes and dynamics of the ice sheets. And that has a threshold somewhere between 0.9 and 0.9 degrees Celsius and 2.5 degrees Celsius, say, relative to pre-industrial. That is, we're at the lower end of that limit already. Our assessment was that the upper threshold could be as high as 4 degrees Celsius and as low as about 1 degree Celsius above pre-industrial. But I think that's an urgent issue that needs much greater quantification of what that is. The Antarctic contribution, 1.2 meters per degree Celsius, and then if you put all those together, you're talking about meters of sea level rise, many meters of sea level rise, even for the 2 degrees Celsius temperature that we're talking about by 2100. These values won't be reached in 2100, but that's the destination which we're heading towards. And there'll be an article coming out, I think, in Nature in the next few weeks, which will talk about these issues. Some recent work, there's been quite a bit of work done since the AR5 on trying to directly attribute the sea level change. This is some work that my postdoc has been doing, Amy Slangen, which is currently in review. The top left-hand panel here is the natural contributions to sea level change during the 21st century. The radiative forcing components are shown by the green lines and the average of the many different models by this black line. So these are a percentage of the actual observed change over this period. If you include in that the idea that the sea level and the glaciers in particular were not in equilibrium with the climate system at the start of the 20th century, and similarly the Greenland ice sheet, then you actually get a greater contribution shown by these grey lines up here of the natural contribution to sea level during the early part of the 20th century is quite significant, but during the latter part of the 20th century it's quite small. The anthropogenic component, in contrast, is relatively small, the order of 20% during the first half of the 20th century, and then rises steadily during the latter part of the 20th century, and from about 1970 on, it's the majority of the contribution to sea level rise coming from greenhouse gas forcing. Doesn't explain all of the rise, even in the last couple of decades. There is a contribution from natural processes that is important to be able to capture the increased rate of rise over the last couple of decades. Okay, so I was going to spend a few moments talking about what I think our requirements are from this community. So reference frames, vertical land motion, these are critically important issues. As a user, the rate of sea level rise currently is of the order of 2 millimeters per year, 3 millimeters per year with the altimeter record. Now, into the future, the amount of rise is going to be much larger. But building our understanding of the process really relies on looking at the past changes and how they evolved and trying to explain those. So I think that implies that we need to understand those rates of change to the order of to better than 10% of the global average rate. So that implies a change, understanding land motion, reference frame issues, and local sea level measurements to the order of 0.2 millimeters per year. Similarly for altimetry, particularly in global mean sea level change, maybe locally, regionally, we can relax that requirement somewhat, but if we need to understand the differences between local observations and satellite observations, again, we need to push these systems as hard as we possibly can. Tide gauge movements, I think the TIGA program and having greater number of direct estimates of vertical land motions at tide gauges around the world is critically important. And it's important to remember that we need to have the ties between those GPS sites and the tide gauges and any local benchmarks. I'm particularly interested in the rates. I think the absolute heights will become more important into the future, and we'll start to put the different observations into an absolute reference frame and not just the rates of change. A couple of examples. Chris will talk about this in more detail later on, but Chris has done a calibration of the satellite, calibration, is that the correct word? Verification of the satellite altimeter record using tide gauges around the world. And it's clear to us that there is some bias in the TOPEX record, the early part of the record, of perhaps a millimeter per year. Exactly what that is depends on how you correct for that vertical land motion, and if you use the GPS velocities, or if there is no GPS velocities, you use GIA plus the elastic motions, then you're talking about corrections to that first half of the record of 1.5 millimeters per year. So this is quite a substantial change. I think this remains somewhat controversial. Is this correct? And if so, what should we do about it? How do we identify the underlying issue with the altimeter record and correct that such that we have greater confidence going forward? If you take those rates obtained by the bias drift and correct the satellite altimeter record, then you end up with a somewhat reduced rate of rise over the period, somewhere between 2.6 to 2.9 millimeters per year, depending on which of those vertical land motion corrections you use. And you change the acceleration from what was previously a deceleration in the satellite altimeter record, not significant, but you change it to a positive acceleration, again not significant. The change is significant, but neither the acceleration or the deceleration themselves are significant. As the record gets longer, so even since this paper was published, we've got another 18 months of altimeter data. The acceleration is getting larger, and it's, I think, still not quite significant, but it's approaching that point where it will become statistically significant. So that's one very important application. This just shows a comparison of the original record in blue and the corrected record using GPS and GIA in purple. Another important application is for correcting land motion of tide gauges. So people like myself and many other people who've analysed tide gauge data have generally used GIA corrections to take out the vertical land motion. Guy Woppelman has shown the value of using GPS data, and I think there should be a greater uptake by that from the community, which means easy access to GPS rates to be able to do that. I think there remains a question, while it's clear that regionally that results in a decrease in the spread in particular regions, there remain significant differences between regions. Is that real, or is there a component in that which is related to reference frame issues or GPS issues? I don't know the answer to that, but I think that's a good issue for this community to address. Guy has taken those rates and applied them to the long tide gauge records, and his estimates for the long 20th century rates of rise are shown here. A larger rate of rise in the northern hemisphere compared to the southern hemisphere. This doesn't seem consistent with what we're learning from the satellite altimeter record and the ocean observations, but it is a different period. When I plot these, just scale these off his results and plot them versus the signal latitude, I get approximately linear relationship, which makes me sort of suspicious of whether there are underlying issues here or not. One of the important challenges, I think, is to get extra handles on the ice sheet contributions, particularly the Antarctic Ice Sheet contribution. So that will result in a fingerprint in the sea level, and this is an attempt by Sarah Perkey and others to look at that mass contribution. So shown on the vertical axis is the sea level trend. So what is it? So they take the oceanographic component, that's the ocean thermal expansion, subtract that from the altimeter and plot that on the vertical axis. So it's an estimate of the mass from an indirect estimate of the mass contribution at each location, and compare that with the GRACE observations, which are a direct estimate of the mass contributions, and they find an approximately linear relationship, but with significant uncertainties. And so one of the challenges, I think, is can we use this type of technique to back out what the ice sheet contributions have to be through their regional distribution? I think that's very challenging. We've tried to do that in the past and completely failed to do it. We can get answers, yes, but do I trust them? No, I'm afraid not. Something we're also focusing on is changes in ocean heat content. Ocean heat content is perhaps the most important variable there is in the climate change debate. So we've been using Argo observations. So there's currently 3,500 Argo observations around the globe. Use these to estimate ocean heat content and therefore thermal expansion of the ocean. So this is an update we've just published in early 2016, showing through the middle part of the water column here, depths roughly from 400 down to 2,000 meters, a steady warming throughout the period. In the upper part of the water column, you see this variability associated with ENSO cycles. If you integrate through the water column, the total heat content or steric rise is almost the same thing with just a proportionality factor between them. A relatively steady rise. These are three different estimates of that thermal ocean heat content change. And this is a much more steady rise, much more indicative of climate change than the surface temperatures, which contain much more variability and are only a tiny contribution to the total heat content of the Earth. Most of this change is occurring in the southern hemisphere with, as I said, a very steady rise at depths from 400 meters to 2,000 meters and much more variability in the surface layer. If you take the satellite altimeter record and the steric sea level rise over this period from 2006 to 2014, and remembering the steric rise is only down to 2,000 meters, and these pictures look remarkably similar, both in the maps and also the zonal averages. So if you subtract those two, this is the field that you end up with. The two, well, perhaps I should just go back and make one point. They have different means. So the altimeter record, the 3.2 millimeters per year, versus the steric rise of the order of 1 millimeter per year, about a third of the total contribution. If you subtract those, then this is the field you get. The two different curves here were blue and green, the thermal expansion and the steric, and there's this significant zonal average difference at high latitudes in the southern hemisphere, which presumably must either be a deep signal beyond the 2,000 meters measured by the Argo floats, and we know there is a signal from repeat hydrographic sections, or it could be a mass signal associated with changes in gravitational field and the ice sheets. To me, this actually looks somewhat similar to this sea level fingerprint from the ice sheets, so perhaps this is worth further exploration. And I think that's the last of my results. Just a quick summary. So in warmer climates, sea level was higher. The rate of rise has increased from pre-industrial through the 20th century and continues to increase. Sea level rise during the 21st century was a rate of about 1.7 millimeters per year and 19 centimeters over 1901 to 2010. We approximately understand the reasons for that. Thermal expansion and glacier contributions are the two largest sources. It's very likely that sea level will rise at an increased rate under all scenarios during the 21st century, with the amount of rise ranging from 28 to 61 centimeters with the low emissions and 53 to 98 centimeters for unmitigated emissions. Only the collapse of the Antarctic Ice Sheet, our estimate was only the collapse of the Antarctic Ice Sheet could lead to a significantly larger rise than our central range, and we estimated that to be no more than several tenths of a meter, and I think that's actually been confirmed, and in fact subsequent studies have shown that we're probably in the lower part of that range. Most of the coastlines around the world will experience sea level rise within 20% of the global mean. It's only the some high latitude regions which will be quite different. I haven't talked about it at all, but clearly there's a major impact in the frequency return period of extreme events. Sea level will continue to rise for many centuries beyond 2100, with the amount of rise dependent on future emissions. Area of significance uncertainties remain, particularly associated with the ice sheets, particularly the Antarctic ice sheets, and there are very demanding requirements, I believe, on this community to help us better understand the reasons for that rise and how it might evolve into the future. So thank you.